In progress.
Hey there. We're going to look at a short video on how cylindrical shells work so that we can spend class time doing a bunch of examples. So just want to give a little example. Let's say we had like a box. It's like say this is 2 and this is 4. So y equals 4, y equals 4, x equals 2. And we're going to use x equals 0 and y equals 0 as our region. And we're going to rotate it around the y-axis. So what we end up with is a cylinder that's got a radius of 2. That's our x right here. And it's got a height of 4. Okay. So normally when we would do something like this, I'll sketch it coming over here, act like it's coming over here. And we know it's a circle. So to get the disk method, we would have to do integrate upwards. So disk would give us a dy. Doing the disk method gives us a dy. What if you don't like dy, or what if there's a better way? What if doing this method gives you an ugly formula? In a cylinder, it doesn't, but this method, cylindrical shell, works on anything. I thought it might be easiest to show you with just a cylinder to start with. So rather than doing disk slices like this is doing a disk slice for dy, instead, let's do something with dx. So let's look at the cylinder from overhead. It's just a circle, right? So what we can do, this is like x, and y is coming out of the page towards us. So x here, the radius is 2. So rather than doing the disc, what we're going to do is we're going to just make little cylinders that keep getting larger and larger and larger, and we go outward or inward. But that way we're doing, at any given time, we're doing this cylinder. And if I sketch my circle over here like this, and my cylinder again like this, what we have is a cylinder. Well, it's a shell of a cylinder. It's not the full cylinder that we're doing. And we slowly do all these cylinders getting wider and wider and wider. Okay. It kind of looks a lot like nesting dolls. So I have a video for nesting dolls I thought you might appreciate. So let's say this little guy is our inner cylinder here. And then this one is just inside the next cylinder. And this is inside our next cylinder. And it keeps going like this. And so we're doing cylinders going outward. Now it's not stacking up like this. It's just going outward. But I think you can help. I think this helps get the picture going on. So how would that work? Well, this cylinder here, this red cylinder, let me draw it a little bit bigger. This is somewhere inside our figure. So it clearly has a height. We've got a height here. We have an outer radius here. Let's call the outer radius R. And a big R, capital R. And let's call the inner radius little r. So if we were looking at the volume of this, we could take the big cylinder and subtract the little cylinder. So the volume of the big cylinder is pi r squared, the area of the circle times the height, minus the volume of the little cylinder, which is the area of its circle times the height. Well, we could do some manipulation here. And we do one more thing that makes it help clear it out a little bit. I'm going to multiply this by 2 over 2. I'm going to move the 2 in the denominator inside this one. And I'm going to move the 2 there out front. So I get 2 pi r minus r, big R plus little r over 2 times h. Well, r minus r is this. That's r minus r. So this is like the width. This is like dr. And when we take two things and add them up and divide by 2, this is actually the average. So this would be like an average radius, which is helpful if we're trying to do integration and we make this a really super thin shell. So like maybe this is r star. And r star is, wow, I didn't do that from the center very well. There we go. I'll put it up here. Nope. Let's put it right there. R star is like halfway between kind of thing. So I could rewrite this as, I think you'll like this. Volume equals 2 pi. We had r star, that was our average radius. We had our height, and then a dr. So if our cylinders are going like this, outward like this, then r is that way, and so dr is the same as dx. So the shells method lets us do a dx here, where the disk method would use a dy. Alternatively, if we had our cylinder going like this, and we're doing rings here, shells going outward here, normally this disk would be a dx, but now our radius is going upward, so it's a y. So dr here would be a dy for the shells method. So let's take a look at a problem and look at it both ways. We'll do one method when one is the other. Let's do y equals x. Y equals x cubed. We'll go from 0 is less than equal to x, less than or equal to 1, and we'll rotate around y. Around y. So that's y equals x. And they're going to intersect. Where do they intersect? X cubed equals x. X cubed minus x equals 0. X times x squared minus 1 equals 0. X equals 0 or plus or minus 1. In our area of concern, it's only 0 and 1. X cubed is actually below it. So that's the y equals x cubed line. So, and then we rotate this around the y-axis. So now what we're going to do is we'll start with the shells method. Assuming these are the same height. I'm not the best sketcher, but we're doing a shell like this. It doesn't matter that here, the inside of that cone is empty, because this is the green region is what we're doing. It doesn't matter because that the inside of the cone is empty because the shell is just doing little vertical slices. So let's take a look at what we're wanting to find the volume. We want to integrate this. So like the radius here is x. So we're going to go along x, 0 to 1. We have 2 pi, right? We're at 2 pi. We got our radius x. What's our height? Our height is this little piece right here. It doesn't go all the way down. So it's x minus x cubed. So we finish this. I'll distribute here. We've got x squared minus x to the 4th dx. This gives us 2 pi times 1/3 x cubed minus 1/5 x to the 5th from x equals 0 to x equals 1. When we stick in 1, we get 1/3 minus 1/5. When we stick in 0, we get 0 minus 0. This is 5/15 minus 3/15. So 2 pi times 2/15 is 4 pi over 15. That's the volume of that area. That's how the shells method works. You're just going outward. You're making larger shells each time. Let's take a look at what we would get using the disc and washer method here. So I'm going to leave that picture up where we can access it, because I'll do a little disc slice here to simulate what we're doing. A disc slice is doing this. So this isn't, the disc is actually going to be a washer, because that hollow spot does matter now. So here, this method's going along dy. And we're adding up all of these washers. So the washer is the outer radius minus the inner radius, right? Outer minus inner. But we need it in terms of y because we're going to be integrating upward. So we need a dy. X equals y is already done. When we have y equals x cubed, we can take the cube root of both sides. Y to the 1/3 equals x. And now we've got this. This is our outer one. This is our inner one. So remember when we had a washer, the washer is pi times outer squared minus inner squared. And we're going from 0 to 1 because it's got the same boundaries. by coincidence, because just the functions, it ends up being 0 to 1. We've got pi. Our outer radius is the y to the 1/3. And that needs to get squared. And our inner radius is just y. And that needs to get squared. All right, so let's do that. I have y to the 2/3 minus y squared dy. And so if we integrate this, we got pi. The y goes to the 2/3 goes to the 5/3. Then we use the reciprocal of that, 3/5 there. The y squared goes up to y cubed. We use the reciprocal there. We got that. And we're going from y equals 0 to y equals 1. So when we evaluate, we got pi times, well, sticking in 1 and anything, 1 to any power is just 1. So we got 3/5 minus 1/3. And then we stick in 0, those cancel out. So if I get a common denominator here, I get a 15 on bottom there, multiply by 3, there's 9 up there. Get a common denominator here, so I multiply by 5, there's a 5 up here. This is 4/15. So we've got pi times 4/15, or 4 pi over 15, which is what we had here. So they both get the same answer. This one I think is a little easier to set up. So that's your strategy. Once you practice using cylindrical shells, once you know how to use cylindrical shells, and the disc washer method, your strategy should be this. Set it up both ways to see which is easier to integrate. Eventually, you'll get a nice feel for it and go, yeah, this method's definitely better for shells. And this one's definitely better for washers. Okay, that's it for the mini lecture. In class, we'll do a bunch of examples. Peace.